So at periodicity, we have that repeating pattern of properties happening on our periodic table. So that's the way it's arranged. There are two main reasons for the trends that we see, and it depends on if the elements are in the same group or the same period. Effective nuclear charge, and hopefully you remember that nuclear charge is simply the number of protons, is how we explain things when the elements are in the same period or row. So you're moving across. They have the same number of energy levels. As you add more protons, they're attracting those electrons better, or they're attracting them more. That attraction is greater. So in our picture here, that's what this blue arrow is representing. That's the effective nuclear charge, that ability to pull those electrons in. Now, if the elements are in the same group, then we talk about shielding. And so the inner electrons, all right, which would be these three right here, are blocking the outer electrons from the nucleus. So they're shielding. And that attraction then to the outer electrons is weakened because of this shielding by the inner electrons. So when you come across a question that's asking about the trends and comparing elements, you really have to be careful about your word choice, and you want to use effective nuclear charge if they're within the same period or row, or shielding if we're talking about them in the same group. So the first trend we have is probably the most important, and it kind of explains all the other trends, is atomic radius. Now there's different ways of defining atomic radius. The first way is to say that it's the measure of half the distance between neighboring nuclei. It can also be thought about as the distance from the nucleus to the outermost electrons, or the valence electrons. But it's really just the size of the atom. All right, the values are actually given to you in the data booklet in section 9. We don't really tend to use those values, but they are there, and so you might see a question that's referring to them. As you're going down a group, the reason why the atoms are getting larger is because you're adding energy levels. All right, you are increasing the shielding, which decreases that attraction to the nucleus, so the atom's getting larger. As we go across the period, we can see that it's getting smaller, and the reason it's getting smaller is because you're increasing the effective nuclear charge. And so you have more protons pulling on those electrons. There's no additional shielding, so that attraction just keeps getting larger and larger, and it's pulling those electrons towards the nucleus easier or better. All right, ionic radius is kind of related to atomic radius because you have that parent atom of what it is when it's neutral, and then you have to look at what happens when you gain or lose electrons. So positive atoms or ions, hopefully you remember that they are called cations, lose electrons. And so what we see is that whole valence shell disappears. So if we look at the picture here, these first three columns are your cations, groups 1, 2, and 13. And so what happens is that parent atom, which is represented by the gray shell, is larger than the red shell, which is what it ends up being once it loses that valence electron. So positive ions become smaller because they're losing that valence shell. Negative ions are your anions, and we are gaining electrons. And so what happens is that effective nuclear charge starts to weaken because you're adding more negatives, and so there's not as much attraction between the positive and negative when you have more negatives. So it's allowing that energy level to kind of expand a little bit. And so we can look at groups 16 and 17 here, and that blue shell, which is your anion, is getting larger than that gray parent atom. Positive ions, if you notice, they're decreasing as you go from groups 1 through 13. and that's because of the larger effective nuclear charge. So boron here has more protons, less electrons in ratio, and so it's going to be able to reduce in size even more so than the lithium ion. As you go from groups 16 to 17, it's getting smaller because it's a larger effective nuclear charge. So again, you have more protons, so they're able to pull those electrons in a little bit easier. If we look down a group, we're still increasing, and that's because you're adding those energy levels. Ionization energy, we're taking that outermost electron and we're going to remove it. So ionization energy is the energy needed to remove one electron. The atom has to be in the gaseous state. So sometimes you might see the definition refer to 1 mole of a gaseous atom. So it has to be a gas, and then you're always going to add energy, and the amount of energy that's needed is what ionization energy is. So energy needed to remove 1 electron. These values are given to you in section 8 of your data booklet, so sometimes it might mention that, but we don't really use the values for anything. As you increase across a period, you're increasing that effective nuclear charge. So you have that nucleus, you have that electron that's out here. There's a strong attraction happening, effective nuclear charge. So it's going to require more energy to pull off that electron, pull it away from that nucleus. But when you go down a group, since you are increasing shielding, you actually have lower ionization energy. So if we have a bunch of energy levels and then our electron sitting way out here, we're not really attracted to the nucleus, so that's going to require less energy to remove it. Now there are some exceptions, just like there were exceptions with our electron configuration. So group 13 is actually lower than group 2. We're ignoring the transition metals because that's a whole nother ball game. But group 13 is lower than group 2, and the reason why is because group 2 has a full S sublevel. So if we think about it, it has these 2 paired electrons, right? And that's going to be more stable than having just a single electron in the P. So group 13 is able to lose that lone electron in the P sublevel easier than group 2 can lose one of its paired electrons. We see this same phenomenon happen at group 15. So group 15 has a half-filled P sublevel. And so for group 15, the P sublevel has 3 electrons in it, and they're all unpaired, where group 16 has 1 paired electron, or 1 pair of electrons, and then 2 unpaired. So group 16 is going to lose that odd man out, that odd electron that's paired, easier than it would, group 15 would lose one of its 3 unpaired electrons. So full and half-filled sublevels are just a little bit more stable. It is the reverse of the trend. So if we're just looking at the periodic table, we would say that the lower left is larger, so we're increasing atomic radius towards the lower left, but for ionization energy, the lower left is lower ionization energy, so it decreases towards the left.